In this video, we'll talk about implicit differentiation, what it is and why it might be useful to help solve problems. Let's start with this example. Consider the circle x squared plus y squared equals 25. We know that the point 3, 4 is on this circle because 3 squared is 9, 4 squared is 16, they added 25. What is the equation of the tangent line at this point? To find this, the one thing I really need is the slope of this tangent line. Once I have the slope, I have the point 3, 4, I can find the equation, no big deal. So what's the slope? Well, there are a couple ways we could do this. The first way is by geometry. So if I draw the circle, the point 3, 4 is somewhere over here. One fact we know from geometry is that the radius to a given point is always perpendicular to the line tangent to the circle. We know how to find the slope of the radius. That's just by rise over run. So the change in y is 4 minus 0, taking the point and the origins of my 2 points here. The change in x is 3 minus 0, so the slope here is 4/3, which means that my tangent line has slope equal to negative 3/4 because it's negative reciprocal. We can also find this using calculus. The main thing I need is I need y as a function of x to be able to take derivatives. So if I have x squared plus y squared equals 25, I can solve out for y to get the function I want to differentiate to find the slope. So if I do that, I get that y squared is 25 minus x squared, or y is plus or minus square root of 25 minus x squared. Now in this case, I want the plus square root, not the minus, because the plus part traces out the top half of the curve, and the minus square root traces out the bottom half. The function I actually want here is the positive square root, so I'll get rid of that. Now we can just find the derivative here. That's going to involve a chain rule because I have a square root on the outside and then a function on the inside. So my y prime here is going to be, derivative of the outside is 1/2 times 1 over square root of u, square root of 25 minus x squared, times the derivative of the inside, which is a minus 2x. The 2's will cancel, and I get a formula for the derivative as y prime is negative x over root 25 minus x squared. My point here was that x equals 3. I plug in 3, I get a minus 3 on top, and the bottom is a 25 minus 9, root 16, which is 3/4, same slope we got before. How else could we have done this problem? Well, we know how to do the chain rule now. So what we can do is just take the expression we had at the start, x squared plus y squared equals 25. And we want to think about y as a function of x. So it is this function that we solved for above, this square root of 25 minus x squared, but I can leave it and not actually solve it out for it first. I know that y is a function of x, which means I can now differentiate this entire equation here in x. So I can apply a derivative to the entire equation here. For the first term, that is just an x squared, so that just becomes a 2x. What about the second term? That's a y squared. So it's not just going to be 2y, because y is a function of x. This is a chain rule derivative here. What am I going to get? Well, the derivative of the outside function is something squared, so it's going to be 2 times y, because I have to plug in the y that I have my function in, and then times the derivative of y, or a dy dx. On the right-hand side, that's a constant, so I get 0, and now I can solve out for dy dx in this expression here. I can move the 2x to the other side, 2y dy dx equals minus 2x. I can cancel some 2's from both sides, and then divide by y to get that dy dx is negative x over y. This expression now involves both x and y, but that's okay, it's allowed to, because I'm told what point I'm looking at. I'm looking at the point 3, 4, and if I plug this in, I again get negative 3/4, the same slope as before. So any way you approach this problem, the slope is going to be the same, which is what it should be because it's still the slope of the same tangent line. Note that for this part though, I did not have to split up into the positive and negative parts of this graph. This works no matter what values of x and y I plug in. So if I wanted the tangent line at, say, 3 minus 4, that's going to be below. I can plug that in as well, and I'll get a slope of 3/4 for that line without having to redo the calculations. If I wanted to go to 3 minus 4 for the way I did before, I would have to redo this with the minus sign in here, and resolve the problem out that way to get the answer. I'd still get 3/4, but I have to redo the calculation to get there. That's the idea of implicit differentiation. The goal of it is that I want to find derivatives or slopes of tangent lines for functions where y is defined implicitly in terms of x. Now, what does that word there mean? Well, it's in contrast to explicit functions. So an explicit function is when you have y equals f of x, the y is by itself on one side, and all the x's are on the other side. An implicit function is sort of when the x's and y's are intermingled in more complicated ways. So in the most general form, it's written as f of x, y equals 0. I have some combination of x's and y's. They can multiply each other. They can be inside other functions. Really weird things can happen there. But I just have whatever combination I want equals 0, equals a number, equals something else on the other side. So I want to take these functions and find tangent lines that way. These functions generally define curves in the plane. And like circles, it may not be possible to write y as a function of x for this curve, which is why we want this method as well to find these derivatives, so I can still find tangent lines even if I can't solve this expression here for y. Let's see one more example here. Here is a case where you cannot solve out for y. Right, you could try to manipulate things a little bit, but there's no way you're going to get y equals stuff in terms of x for this equation because there's that fourth power there. So I want to find the derivative of y with respect to x if y to the fourth minus y equals x cubed plus x. So what I want to do here is just take the derivative of the entire expression. What does that give me? Well, the y to the fourth is going to become a 4y cubed times a dy dx by the chain rule. Something to the fourth becomes 4 that something cubed times a dy dx. The minus y becomes a minus dy dx. And this equals, the right side only has x in it, so it's going to differentiate normally, 3x squared plus 1. And now I can solve out for dy dx. Dy dx times 4y cubed minus 1 equals 3x squared plus 1, or dy dx equals 3x squared plus 1 divided by 4y cubed minus 1. Again, these derivatives involve both x and y, but that's totally fine. You have to be given a point in terms of both x and y to figure out what tangent line you actually want. That's the idea of the process, why it might be useful, and how you can use it to solve simple problems with implicit differentiation.